Another quick intro video to this lesson. These are the 1.1 notes on the nature of science. Again, they're posted in Edpuzzle so I can monitor your progress. Also, during these notes, you'll find formative questions in the middle of the notes, so those will be posted in Edpuzzle as well. The format of these notes are set up so that in Canvas, you have the notes that you can download into Notability and then fill in those notes as you're watching the video. The notes are where you'll find the information necessary to study for your assessments. So your unit tests and quizzes will come from the notes. So it's important that you're watching the videos and finishing the notes. You'll get credit for completing this video assignment by watching it in its entirety and answering all the formative questions. I'm still working out the technical details of making videos for my lessons, so please forgive any editing hiccups that might occur, and just watch the video and do the best you can with the quality and the audio. If you have any questions, comments, and concerns, please feel free to email me or attend one of my Zoom office hours.
All right, so today what we're going to be starting to talk about is the nature of science. That is the process that scientists use in order to go through investigations and learn new things. Okay? So this is not talking specifically about biology as much as science in general. So these are things that apply to all sciences. So the first thing we have here is our priority standard. Remember, your priority standards are the main topic that we're trying to master in this particular unit. Okay, so the priority standard here is to use concepts to solve scientific problems using the scientific method and elements of scientific inquiry, and draw conclusions to scientific problems from qualitative and quantitative data. So there's a lot going on there, okay, and we're going to kind of break it down and go through all those little pieces. Today we're going to focus specifically on scientific inquiry and the scientific method, and we are going to actually continue this on Friday. So this is the topic, the idea that we're trying to master here. Okay, so on this first page, you're going to see blanks in your notes, so you want to make sure that you fill in the blanks where necessary. So starting off here, one of the things that I notice when students walk into a science class, or when anybody for that matter opens up like a science book or reads a scientific paper, is they come across a lot of vocabulary. They come across words like photosynthesis and deoxyribonucleic acid. And they say to themselves, well, I don't know what those words mean. Close the book. I must not be smart enough to learn science. Well, see, this is a problem, because I don't think for a moment that you're not smart enough. I think the problem is you just don't understand the words of science. Okay. Something that a lot of people don't talk about and don't understand really well is that when you learn new words and you use those words in conversation, okay, it makes you sound smart, right? So if somebody's really talkative, you could call them talkative, or you could call them loquacious. The word loquacious means talkative. It's just another way of saying it. So if you say, you know, that's a really loquacious person right there, people are going to look at you and think, well, that's a complicated word. That's a pretty smart person right there. So by learning new words and using those new words, you sound smarter, right? Well, here's the real trick. Is not only do you sound smarter, you are actually smarter. Because a lot of intelligence is based on language. It's your understanding of language. Think about it. What's the difference between a book that a kindergartner would read and the book, like, say, an 8th grader would read? And yeah, we could talk about, like, subject matter and, like, pictures versus no pictures. But the biggest thing is language. Okay? Kindergartners just don't know enough words to understand what an 8th grader would be reading about. Okay? It's more words makes you smarter. And the more complicated words you know, literally the smarter you are. So a lot of the pursuit of science and people's opinion on science really comes down to the language. It comes down to, do I know those words? So something that I'm going to do throughout the year, something that I point out all the time, is how we get these science words. A lot of people will open a science textbook and say to themselves, it's like they're speaking another language here. And they kind of are. A lot of science root words and prefixes and suffixes are based in Latin and Greek. Okay, so literally we are speaking in another language. There's a lot of kind of scientific tradition that comes from Greek philosophers and Latin-speaking scientists. So we do use Greek and Latin quite a bit in the language of science. So I like to break these words down so that it makes more sense. And therefore, you learning new words, you are becoming smarter in the process. So the word science, in general, comes from the root word psi, which is Greek, which means to know, or simply knowledge. So science is the pursuit of knowledge. And we use the word science in a lot of different respects. Okay, so if you go to your history class, we might say you're learning social sciences. That is, the knowledge of society. If you pay attention to politics, we can say you're interested in political sciences. That's the knowledge of politics. So in this class, specifically, we are more interested in what is called the natural sciences. That is, the science of nature, okay, and how the world works. But you can see that prefix psi used in a lot of different places. So like the example here, conscious, conscious, you wouldn't pronounce it that way, but to be conscious means to be awake, to be aware. Basically, able to obtain knowledge. You have to be conscious to get knowledge. Okay, then the word disciple, psi is right there. A disciple is someone that is pursuing a certain kind of knowledge or a certain topic of knowledge. So if someone says you are a disciple of something, they're saying you are pursuing knowledge of that something. Okay, so science in general is just the pursuit of knowledge. So when we are talking about science in this class, we are talking about the natural sciences, the pursuit of knowledge of the natural world. Okay. So anything related to the natural world could be considered a natural science. And that, of course, applies here. Biology, we are pursuing knowledge about life. What makes something alive, what keeps something alive, and everything that's surrounding that living thing. So, in the pursuit of knowledge of the natural world, in pursuit of sciences, there are certain procedures, certain methodologies that we use to gain that knowledge. And one of the things that scientists are constantly thinking about in terms of that knowledge is how reliable is that knowledge? Can we trust that that knowledge that we have is accurate, is true? And one could say that scientists are pursuing truth. We are looking for the truth of things. Okay? But we need to make sure that we are always checking. We're always proving to ourselves that what we know is something that's actually true. Okay? And scientists are constantly checking and rechecking their ideas to make sure this is that they are accurate as possible. Okay? So we use the processes of scientific investigation and observation to try to gain this knowledge. And there's a couple different ways that we can go about doing that. And that's kind of what we're focusing on today. But before we get to that, okay, science is a very broad category. So to make things a little bit easier to digest, a little bit easier to pursue, we break sciences down into different disciplines. Okay? And there are three major disciplines of the natural sciences. Okay? And each discipline kind of has its own focus. So we, of course, in biology class, we are interested in life science. This is the study of living things, living organisms. What makes a living organism and all the things that keeps that organism alive, all the things that surrounds that living organism. Probably last year, you were studying earth science, or what is sometimes referred to as earth space science. This is, of course, the study of the earth and the planets and the stars and the space and the cosmos and the universe in general. Okay. And then we have physical science. Physical sciences are the study of the matter and the energy that makes up the earth and the universe in general. Okay. And physical science incorporates things like chemistry and physics. But also things like engineering falls into the physical science. Okay. There's a lot of cross-play within these disciplines. So if you're interested in life, it's really hard to study life without studying the Earth that this life is found on. As far as we know, there's only life on Earth. Okay? Now, scientists are actively pursuing, okay, is there life anywhere else in the universe? But right now, it's just on Earth. So it's hard to study life without knowing at least a little bit about the Earth. And if you're studying the Earth, well, you're going to realize that the Earth is made out of matter. It's made out of energy. Okay? So we need to have a little bit of physical science in there. And then, well, living things are made out of matter, and living things have energy. We can't study one without getting into a little bit of the others as well. In fact, the next unit, Unit 2, and we're actually going to be talking a little bit about chemistry, because it's really hard to understand life without understanding the chemistry that goes into life. So we'll get into that a little bit as well. So the first question, if you were interested in designing cars that are safer during automobile accidents, which discipline of science would you be pursuing? B is the correct answer, physical science, because think about what's involved here. So if we have a car, cars are made out of matter. Okay? To make the car move, you need energy. Okay? But more importantly, if that car gets into an accident, all that matter and all that energy comes to a sudden stop. Okay? And if you're inside of that car, then that sudden stop is going to have an effect on you. So scientists, engineers, spend a lot of time trying to figure out, okay, if that car comes to a stop very suddenly, how can we keep the people inside from going squish? And that's where seatbelts and airbags and all that comes from. Okay, so that's a pursuit of physical science. Now, one could argue, well, if there are people inside that car, well, there's a little bit of life science going on there too. And yes, we do take that into consideration. Okay, so again, there's a lot of kind of cross-play within these disciplines. All right. So, in order to gain the knowledge in any one of these disciplines, we're going to have a process. Okay? These processes are going to allow us to gain the knowledge that we need. And one of those processes is what we call scientific inquiry. Okay? This is the process of asking meaningful questions and then looking for answers to those questions. One of the things that I always say when it comes to classes, science classes, is that one of my goals for my students is to make you think more like a scientist. Okay? And I'm not saying you're going to be some sort of nerd wearing a lab coat in a laboratory or anything like that. I'm saying to think more like a scientist rather than thinking like, you know, a normal person. So a normal person would look and say, oh, there's a thing that's weird and I don't understand. A scientist would say, oh, there's a thing that's weird and I don't understand. Let me go figure it out. That's basically it. That's the difference between a scientist and a normal person. Is a scientist is actually going to pursue answers to questions. Scientists are the sort that are curious enough and motivated enough to try to find answers to questions and to solve problems. Okay. Now, you do this on kind of a regular basis anyways. You don't think of it as, hey, I'm going to do a science, but you're constantly confronted with problems or questions that you need solutions for. And you go about trying to do that the best you can. Okay. And so a lot of us use scientific inquiry without even realizing that that's what we're doing. Okay. So let's say you have a problem. Okay. And granted, we have quarantine and COVID and stuff like that to deal with. But let's say, for example, you want to go to the movies. Let's say the movie theaters are open. You want to go to the movies with your friends. It's Friday night. I want to go out with my friends. So you go to mom and dad and say, hey, I'm going to go out to the movies with my friends. Your parents go, no, you're not. Look at your bedroom. It is a mess. There is clothes and garbage everywhere. Before you can go out and have any fun, you need to clean your room. Okay, so you have a problem. I want to go out, but my room is a mess. So you sit there and think to yourself, well, let's do some science. Well, no, you don't. You think to yourself, okay, how do I clean this room quickly and get it done so I can go out and have fun? Okay. So you're going to go through a process. You're going to think, I have a problem. Maybe I could just shove everything under the bed. Well, that doesn't work because now the bed is 10 feet in the air and it's pretty obvious that all my junk is over there. So, okay, shoving it under the bed doesn't work. Okay, maybe I can take everything and shove it in the closet. Well, I can barely get the closet door shut. Okay, that's not going to work either. So you sit there and think for a moment, okay, well, I can put some of the stuff under the bed, some of the stuff in the closet, and here's some clothes. I can shove it in the dresser. Okay, they don't fit. Well, maybe if I fold them nicely, okay, now they fit in the drawer. And the garbage that's on the floor, all the pizza boxes and candy wrappers, okay, those can go in the trash. I don't need those in my room. Okay, and then you clean your room and you say, can I go out now? Your parents look and say, okay, yeah, it's clean, you can go. What you just did was scientific inquiry. Now, you didn't think of it that way, but that's what you did. You had a problem, you found a solution to that problem. Okay? And along the way, you had to figure things out as you were going. Okay? Scientific inquiry is more fluid and non-linear of a process, meaning that you can take twists and turns down the road as you're going. And this is what we would commonly think of as trial and error. We have an idea, we try that idea. If it doesn't work, we try something new. Okay? And you may not think about this process, and this process might be kind of instantaneous in your brain. So it's like, okay, what do? I'll do this, and then you go about doing it. Okay? So the process of the scientific inquiry is a way that scientists can kind of quickly try to come up with solutions to problems. And again, this is something we do on an everyday basis. We just kind of don't realize that that's what we're doing. Okay? So the first step, and we say step, but scientific inquiry is not really tied to step-by-step processes. But the first step is to identify the problem. Okay? What is it that I got to do? I got to clean my room. Now, you may not sit there and formally write this down. Okay, my problem is... But in your head, you have to know, what is it that I need to know? What is it that I need to do? And in this part of the process, you got to start with what you do know. Well, my room's a mess. And what I need to know. How can I make my room not a mess? Now, it can get a little bit more involved than that if the problem's a little bit more complicated. But we got to identify what is it that has to be done first. The next step is to plan a strategy. That is, come up with an idea of what you're going to do about this problem. Now, if the problem is I got to clean my room, you're not going to sit there with a pad of paper and write out a formal plan. Well, today I'm going to clean my room, and this is how I'm going to do it. No, you're going to, in your brain, like, I'll do this. Now I'll try this, and then this. Okay, so you're planning a strategy. You're coming up with an idea, but you might be doing it on the fly. Okay, it might be happening as you're going. And as you're shoving stuff under your bed or cramming stuff in your closet and you realize, well, that's not working, you're going to change that plan as you go. So scientific inquiry gives you kind of that freedom to try stuff. If that doesn't work, then fix it and try something new. That whole trial and error idea. Okay. Now, there is something to be said about the planning stage. Okay. If you take very little time to plan, there's a good chance that plan won't work. Okay? Now, if you take a little bit more time, kind of slow yourself down and say, okay, instead of just jumping into throwing everything in my closet, maybe I should plan this out a little bit. Okay? I have some stuff that fits easier in the closet, some stuff that might go under the bed easier, maybe these clothing that's dirty needs to go into a laundry hamper. Okay, so if you take a little bit of a time to plan it out, your plan might be a little bit more successful. Now, there is a kind of a flip side to that as well. Okay, if you spend all your time planning, then you're never going to get to the next step, okay, which is to execute your plan, to actually make it happen. Okay. Now, in the world of scientific inquiry, the planning and the executing might happen very quickly. Here's my idea, let's jump in and do it. Okay. Again, if you spend more time planning, there's a greater chance that your execution will be successful. Okay. But if you never get to the execute stage and you're just sitting there planning, then nothing ever gets done. Once you've executed your plan, the last step is to evaluate your results. Step back, take a look. Is my room clean? It is? Then I can go out. Now, more likely it's like, Mom, Dad, is my room clean enough? Can I go out now? Okay. Now, with the evaluation stage, you're going to have basically one of two results. Either yes, it works, or no, it doesn't. If yes, it works, I'm done, I get to go out with my friends. If no, your room is still filthy, okay, you just shoved a bunch of dirty clothes under the bed, you got to go back and you got to try again. Okay. So the steps of scientific inquiry is to identify your problem, to plan your solution, to execute that plan, and then to evaluate your results. Now, depending on the results, you might need to go back. Okay, so if I evaluate, nope, it didn't work, I might have to go back and identify that problem again. Maybe the problem was not clearly identified, okay, or maybe my first solution caused more problems to show up. Okay, as I picked up the dirty clothes, I realized that there was a bunch of trash underneath the dirty clothes. Okay, that's another problem I got to solve. Okay. But sometimes when you come up with your evaluation, you just got to go back and come up with a new plan. This plan didn't work, I got to go back and I got to try something new. Okay. And you just keep on going through that process until you come up with the solution to your problem. Okay. This is scientific inquiry. It's kind of a less formal process by which we can go about solving problems, answering questions. And this is good on kind of like a day-to-day basis, but when it comes to scientists trying to get thorough knowledge about something, they want to be a little bit more rigorous in their investigations. So, before we get to that, next formative question. So, Kylo's lightsaber stops working. He decided it needs a new power emitter. He removes the old emitter and installs a new one. He switches the lightsaber and checks to see if it's working again. Okay. So, you might notice I'm kind of a Star Wars fan around here. Okay. And this is something that we sometimes get in science, is where you're given a problem and you don't necessarily know all the words in the problem. So if you know nothing about lightsabers or power emitters or anything like that, you might be tempted to say, well, none of that makes sense to me, so I'm going to close the book and I'm just going to give up. Okay? But I could have used any example here. I could have used, instead of Kylo Ren, I could have said Mr. Wassman. Instead of lightsaber, I could have said car. Mr. Wassman's car stops working. I decide that it was the spark plug, okay, which is a part of a car, and I decide to switch out that spark plug, and then I try to start the engine to see if it works again. Now, if you don't know anything about cars, that example may not make any more sense than lightsabers, but still. Okay. But you can still evaluate what's going on with this problem. So, which part of the scientific inquiry is represented by step number 3 here? Okay. So, scientific inquiry is a less formal process, and you can go through it quickly and you can come up with answers to questions. Now, for a scientist, they generally want to be a little bit more deliberate in their process. Okay? And the reason why they want to be more deliberate is because we want to be able to rely on the answers that we come up with. So, let's use a real-life scenario. Okay? COVID-19. We need a vaccine. There are a lot of scientists that are currently working on treatments. They're working on trying to develop a vaccine. Now, if someone came up to you and said, hey, I have this syringe full of stuff. Can I inject it into you? And you could ask, what's in that syringe? And they're like, I don't know, Gatorade, chocolate syrup, some other stuff found in the kitchen. It should work. Yeah, I wouldn't be too thrilled about somebody injecting me with something like that unless they could show me some evidence that it's going to work. Okay, what's the evidence that injecting me with Gatorade is actually going to do anything about COVID-19? Okay. This is what scientists have to confront with. The reason why developing a vaccine takes months, even years, is because they have to have enough information, enough knowledge about this virus, about what happens with the virus, to develop a treatment, to develop that vaccine. And then they want evidence to back up, yeah, this vaccine is going to work. Okay. So by the time someone comes up to you and say, hey, this is a COVID-19 vaccine, we're going to have a lot of data to back up what it is that we're saying. So scientists are more deliberate with their process because they want to make sure that their results are reliable. Okay? When we're pursuing knowledge, scientists want to make sure that the knowledge we're pursuing is accurate, that it's the truth. Okay? So to do that, we need to use a more rigid process. And this is what we call the scientific method. And you're probably already familiar with this a little bit. So the scientific method is a step-by-step process. And the reason why we want to go step-by-step is because we want every scientist to be using the same process over and over and over again. Okay? And the more times we go through that same process, the more reliable the results are going to be. Okay? Scientific inquiry is a lot of trial and error. It's like, does this work? Yes? No? Okay, move on. The scientific method is more about collecting evidence. And we're going to say that a lot in science, is what's the evidence that supports these ideas. This is something that I come across quite often in a class, is we'll talk about some scientific idea and someone will be like, well, how do we know this is true? Well, it's not that a scientist wakes up one morning and says, you know what? I think photosynthesis. Okay, no, a scientist is going to do research and they're going to figure out what's going on inside of a plant that allows them to make food out of sunlight. That's what photosynthesis is. We'll get into that later on in the year. Okay. So what the scientific method is a series of steps that allows us to investigate a single question and be confident that the results are accurate. Okay. So the first step of the scientific method is very similar to the steps of the scientific inquiry in that we got to identify our problem. Now, you've seen the scientific method before, I'm sure. Now, the number of steps and what we call those steps might vary from one teacher or one textbook to another. But it's all the same process. So we call this define the problem. But we might also say identify the problem, or ask a question, or make an observation. All of this is basically deciding what is it that we're trying to understand. What is the knowledge that we are pursuing here? Now sometimes, for a scientist, that question is decided on by themselves. They decide what knowledge they want to pursue. Okay. There's a very famous biologist named Dr. Jane Goodall. She was very interested in the behaviors of chimpanzees. So she decided to pursue the knowledge of understanding chimpanzee behavior. And she actually spent many years living in the jungle with chimpanzees. And there are some people that say, well, I would never do that. Okay, well, that was something she was interested in. She pursued that knowledge. Okay. Now, for those of you that are like, I can't understand why anybody would want to do the science thing. Okay. Same thing can be said about anything. I mean, I know a lot about Star Wars. Okay. I could answer a lot of questions about Star Wars. And some people are like, why would anybody care about anything Star Wars related? Well, I would actually say the same thing about sports. I'm not a big sports fan. Okay. I can tell you all about how to make a lightsaber and kyber crystals and force powers and things like that. But I know there's some people that are sitting out here that could tell me tons of stats about baseball players or free throw averages of basketball players. Like, I don't know any of that stuff, and I don't really care to know that stuff. It's just not a knowledge that I'm interested in pursuing. So when it comes to science, scientists usually pick that pursuit. They pick which knowledge they're interested in following. Just the same way as you pick which sports you're interested in, which movies you're interested in paying attention to. There are people that can tell me everything that you could possibly know about Harry Potter. I mean, I know a little bit about it, but that's not the knowledge that I pursue. So scientists often go off on their own pursuits. So sometimes they choose the questions they're going to answer, but sometimes the problems are put on them. So going back to that idea of COVID-19, okay, scientists didn't choose to come up with a vaccine for COVID-19, but that's a problem we have to solve. So some scientists stepped up and said, you know what, I'll do it. I'll try to find this answer. So that's the first step. We just got to define the problem. The next step is to research the problem. Now this is some place where scientific inquiry and scientific method are different. There's no research inside of inquiry. If you have to clean your bedroom, you're not going to sit down and Google, how do I clean my bedroom? No, you're just going to come up with an idea and jump into it and try to do it. But in the scientific method, research is an important step, okay, for a couple reasons. First of all, if I have a question, I might want to check to see if someone else has answered that question already. Okay? If your question is, why is the sky blue? Well, it would take you about 15 minutes of research to find an answer to that. Because even if you don't know why the sky is blue, there is knowledge. Scientists do know why the sky is blue. We've already done that research. So you can Google that and find an answer. Okay? So if you could just research your problem and find the answer, you're done. Why go any further? Okay? Now, if you do some research and you find, well, nobody has the answer I'm looking for, then now you have to take it a step further. Now, before you go any further, you probably want to be as knowledgeable as possible about that topic. So, again, Jane Goodall, scientists wanted to study chimps. So before she ever went into the jungle to hang out with chimpanzees, she learned as much as she could about biology in general, but chimpanzees in particular. So might be a good idea to know that, you know what, chimps are herbivores. They're plant eaters, so they like eating vegetables. So, okay, the chimps aren't going to try to eat me because I'm not a vegetable. But you might learn that sometimes chimpanzees will attack each other and kill other chimpanzees. Okay, that's something that I might need to know so I can keep myself safe if I'm going to go hanging out with a bunch of chimps. Okay, so you learn all that you could possibly know about that topic. Now, what's interesting about Jane Goodall is that we didn't really know a whole lot about chimpanzee behavior before she started. So sometimes when we're seeking knowledge, we're the trailblazer. We're the person that's going out and figuring this stuff out first. So there's not a whole lot of background to know before we jump in. Okay. But another reason why we want to do research is for step number 3. We want to come up with a hypothesis. Your hypothesis is an educated guess, a solution to your problem. So let's say our question is, why is the sky blue? And your educated guess is, well, there are a bunch of invisible Smurfs floating around in the sky. Well, that's not a very educated guess, because why would there be invisible Smurfs? Okay, so you want to base your hypothesis, your prediction, your guess, in some sort of knowledge, either some sort of observations you've made or some research that you've done. Okay. Now, a mistake that a lot of people will make is they'll say, okay, well, here's my problem. This is my predicted solution to the problem. I'm done. I have a solution. But again, scientists want evidence. They want data to back up their solution. So if someone comes up to me and says, hey, the cure for COVID-19 is taking a cat and rubbing it on your head, well, I'm going to want you to back that up. I want you to show me some evidence that shows that rubbing cats on your head actually does anything to cure a virus. Okay, that kind of indicates to me you don't know how viruses work. Okay. So we want some information to back up that hypothesis. And that's the next step, is that we need to test that hypothesis. And this is a complicated process. We're actually going to get into that next week, talking about experiments. Okay, testing your hypothesis, this is where a scientific experiment comes in. Okay. The experiment is how we test that hypothesis. And there are certain factors that we have to keep into consideration to make an effective experiment. And again, we'll get into that later on. But as you're performing that experiment, as you're testing that hypothesis, you're going to be collecting data. Data are the measurements that you're taking as you're doing those tests. From that data, you start compiling evidence. Evidence is basically the proof that you need to show that your hypothesis works. And that's where we come into step 5. Step 5 is where you're going to analyze your results. So you're going to look at the data you've collected, and you're going to ask yourself, what does this tell me about my problem? What does this tell me about the question I'm trying to answer? And this is the part where scientists are going to do a lot of math. Okay, they're going to solve equations, they're going to make charts and graphs. And what that's going to do is it's going to help them understand the data and look for patterns in that data. Scientists love patterns, because when we can pick out a pattern, that helps us predict the results of the next experiment, or predict what's going to happen next. Okay? So when scientists make observations, sometimes what they'll do is they'll say, okay, where's the pattern here? Because if I have a pattern, I can know what's going to happen next, tomorrow, or the next day, or a year, or 100 years from now. Okay? Scientists have done this for as long as we have recorded history. People know that the sun rises in the east and sets in the west. When the first humans realized, hey, there's a big sun, it goes up and then around and then lands, okay, tomorrow does the same thing. We have observed that process so many times that we can predict down to the minute when the sun is going to rise each morning and when it's going to set each night. Okay? We have observed that pattern over and over and over again. Now, if for some reason that doesn't happen tomorrow, the sun doesn't rise, all of a sudden scientists are going to be really scrambling to try to figure out what's going on. Okay? The final step is to draw your conclusion, to take that analysis, to take that evidence, and then decide what does that mean for the question that I'm trying to answer. And this usually comes in the form of going back to my hypothesis, going back to that guess that I took early on and saying, was my guess right or wrong? So what scientists will often say is that the evidence supports my hypothesis or the evidence does not support my hypothesis. Now scientists say it that way because they don't want to say, well, this is 100% proof, it works, we're done. Because scientists are always questioning results and they always want to go back and test more and more. Okay? So when you draw your conclusion, you need to ask yourself, well, what's going on? Did I answer my question? Now, if the answer to that is no, I didn't answer my question, then maybe I need to go back and come up with a new hypothesis. Or maybe my hypothesis is okay, but I got to go back and design a new experiment to test that hypothesis again. Maybe the experiment was flawed somehow. So scientists are constantly going back and checking their work. Now, if your data shows, yes, my hypothesis seems correct, scientists are still going to go back and test it some more because they want to make sure. So, you know, you see those commercials all the time. Hey, this toothpaste, 4 out of 5 dentists approve. Okay, so why did those dentists approve that toothpaste? Why should I believe you that this is the best toothpaste to use? Okay, so if you come up to me and say, hey, here's a toothpaste, use this, I'd be interested in seeing, well, what do we know about this toothpaste? Well, hey, we had 1,000 people brush their teeth with this for a month, and look how shiny and bright and healthy their teeth are. Well, that'd be pretty convincing. Now, if you say, hey, use this toothpaste, look at this guy, and all his teeth are falling out, yeah, I'd be pretty skeptical about that toothpaste. All right, so next question. You've heard the phrase jumping to a conclusion. Okay? So why would this be problematic when using the scientific method? Why would jumping to your conclusion be a problem? Okay? A, you cannot reach a conclusion without appropriate research or data. B, it's impossible to do the steps out of order. C, a conclusion must be agreed upon by lots of scientists. Or D, the conclusion cannot come after the hypothesis. So why would you not want to jump to your conclusion when it comes to science? How many people say A? How about B? C? D? Of course, the correct answer is A. Okay, you can't reach a conclusion until you've gone through all the steps. Okay, this is like someone coming up with a hypothesis and saying, I'm done. No, we need to go through all the steps one by one because that conclusion has to be based on something. Okay, we can't say, oh, the sky is filled with invisible Smurfs because I said so. Okay, we need some evidence to support that idea if we're going to believe it. Okay. Now, something that a mistake a lot of people make is they'll look at this and say, oh, a conclusion must be agreed upon. We have to agree with the conclusion, okay, for it to be accepted. And that's not necessarily true. Okay. Scientists might like an idea, they might agree on an idea, but unless you have the evidence to back it up, that idea is not worthwhile. There have been plenty of times when scientists have had good ideas and they've had to throw them out the window because the evidence says something else. Yeah. So, when looking at the scientific method, we of course need a hypothesis. So, a little bit more detail on that hypothesis. A hypothesis is a possible answer. It's a predicted answer to your problem. Okay? But it needs to be testable. Okay, so that's a big thing about a hypothesis, is you need to be able to test that hypothesis. And this is the process of experimentation, is that testing process. If you cannot test a hypothesis, then it is not a good hypothesis. And there are plenty of hypotheses that scientists have but can't test, so they just have to leave it there. So the scientific method is stalled at step 3. Say, well, since I can't test this hypothesis, we're kind of stuck. Okay? And it might be a good hypothesis, but unless we have the means to test it, then we can't rely on it. Now, scientists have had this happen before, where we've had good hypotheses, but we didn't have the technology available to test those hypotheses. Okay? Scientists stared at the planets and the stars for many, many years, and they had good ideas about what was going on up there, but until they invented the telescope, they couldn't necessarily investigate any better than just staring up at the sky with their naked eye. Okay? Scientists had ideas about diseases, but until we had tools like the microscope, we didn't necessarily know how diseases were carried, how they were transmitted. Okay? So sometimes the technology has to catch up with our ideas. But sometimes those ideas are limited by where we are. There are a lot of astronomers that stare up at the planets and the stars and they have some great ideas, but I can't hop into a rocket ship and go millions of light years away. It's just not possible. Okay? So we have to be stuck with just ideas. So unless we can test that hypothesis, it's not a very good hypothesis. Okay? A sound hypothesis is going to be based on observation and research. So again, this is why step 2, doing that research, is important. It's because we need some knowledge in order to have an educated guess. Education is the pursuit of knowledge, so to have an educated guess, we need to have done some research. Now, your hypothesis can be based on the stuff you already know and the stuff you can see. So you could be observing something in nature and say, you know what, that seems reasonable. Okay, do a little bit of research. So based on both that research and those observations, you can come up with a reasonable hypothesis.